Assalamu alaikum. So inshallah today I'm just trying to revise how to use a steam table or steam or refrigeration tables. So we do have two tables, tables for steam and another set of table also for refrigerant 134A, one of the freon which is 134A. For each of those actually two tables we do have three tables. So for steam we do have three tables. One table in the subcooled region or compressed liquid zone, and one table for, or two tables actually for the saturation zone, and one table for the superheated zone. In case of refrigerant 134A, we don't have table for the subcooled region, but we do have two tables in the saturation zone, and also we do have one table for the superheated zone. Just trying to recall actually those zones. If we look actually for the saturation curve on the PV diagram, for both for refrigerant or for steam also, this is actually the saturation curve. At the top of this curve actually we do have, this is a critical point. Pressure is in this case now, the pressure in this case is B critical. This is the critical pressure. And in this case also the temperature in this case is the critical temperature. So at the top of this curve we do have the critical point. The left hand side of this curve we do have the saturated liquid line. In this line actually we do have the quality is equal to 0, x is equal to 0, and we do have this line, the right hand side line represents the saturated vapor line, through which actually we do have the quality of the mixture is equal to 1. The parameter x, or the quality, is the ratio between the mass of vapor or M gas, mass of gas, divided by the total mass, which is mass of fluid plus mass of gas, or mass of liquid plus mass of gas. In the saturated liquid line, just the temperature is equal to the saturation temperature. So we do have the liquid start the boiling process. So in this zone actually we do have the value of quality is equal to 0, because we don't have any gas, mass of gas is equal to 0. After actually the conversion of all liquid into gas, in this case we convert to the saturated vapor line, all of the mass is vapor, and we don't have mass of fluid, so the value of x will equal to 1. Before the saturated liquid line, the state of the substance, let's say in this region, the state of the substance is called subcooled or compressed liquid zone. And actually in this zone between the two lines, the state is saturated mixture. We do have saturated mixture zone. This is actually saturated mixture of liquid plus vapor, and actually in this zone to the right hand side of the saturated vapor line, we do have the state of the substance is the superheated case. Is in the superheated case, so this is actually called the superheated zone. So in each of those zones actually we do have tables. So in the subcooled or compressed liquid zone we do have table, and also we do have tables for the saturated mixture zone when we do have a substance in the saturation zone, and also we do have a third table when we are in the superheated mixture zone. Actually we do have two tables, or two set of tables. One set of table is for steam, and the second set actually is for refrigerant 134A. So for steam, the set of table for steam, we do have, first of all, we do have table A7. This is actually for the subcooled or compressed liquid state of the substance. We can just use table A7. We do have table A4 and table A5 are used actually in the saturation zone when we do have saturated mixture of liquid plus vapor. This mixture is liquid plus vapor substance during the phase change process. And we do have another table which is table A6, which is used actually for the superheated state of the substance. This is regarding steam, and we do have another set of table for refrigerant 134A. For this refrigerant we are using table A11 and table A12 for the saturated mixture state, and we do have table A13 for the superheated state of refrigerant 134A. If we look actually for the saturated mixture zone, we do have two tables for steam, and also for refrigerant we do have two tables. This table A4 for steam is starting with temperature, so if temperature is given, we can use table A4. And table A5 is starting with pressure, so if pressure is given, we can just use table A5. Same case actually is applied for refrigerant. Table A11 is starting with temperature, and table actually A12 is starting with pressure. However, the values are very similar. So if temperature is given, I can just use this table. If pressure is given, I can just use the other table. Right, let's look at the steps. I will just introduce the step how to use the steam table, and it is exactly applied to the case of refrigerant 134A. Instead of actually using table A4 and A5, I will be using A11 and A12. Instead of using table A6 for superheated, I will be using table A13. In case of refrigerant 134A, we don't have table A7. But exactly, I will just introduce the case for steam, but actually the procedures are the same for refrigerant 134A. Right, to use the table, we do have two main cases of given properties, and then we can just proceed. So first of all, so the cases that will be maybe given for you. First case, either it will be given temperature or pressure plus one of the other specific properties, maybe specific volume, specific internal energy, specific enthalpy, or a specific entropy. Okay. Actually, to use any of those tables, we have to have two independent and intensive properties. Two independent and intensive properties. Actually, the specific properties are independent. The specific properties are actually intensive properties. So we do need two intensive and independent properties. So either it will be given actually temperature or pressure with one actually of those specific properties. So in this case, we have to proceed. Let's just erase that. So in this case, if the temperature is given, we will just be going to table A4. This is actually if T is given. So if temperature is given, I will be using table A4, or if the pressure is given, so in this case I will be using table A5 if T is given. Okay, so either pressure or temperature will be given plus one of those specific properties. I will just make the procedure actually if the specific property that is given is the specific volume, but actually it may be any other specific property, maybe internal energy, enthalpy, or entropy, any specific property. Now let's say we are giving temperature and specific volume V. So in this case, using temperature, I will be going to table A4, and in this case I can get actually specific volume of saturated liquid V fluid, and also I can get a specific volume of saturated vapor V gas. Type if temperature is given, well, let's say with internal energy. So in this case, instead of V, I will get U. So it will be U fluid and U gas. Let's say enthalpy is given, it will be the same. I will go to the table with this temperature, get H fluid and H gas. Like this also the entropy. Let's say we do have the volume, I will get V fluid and V gas. In this case, we have to check. Also the same, if pressure is given, I will be going to table A5, and also the same, I will get V fluid and V gas. Then we have to check. Let's say, case A, when we check actually these values of V fluid and V gas with the given value, given a specific volume. So if we do have the given specific volume is less than V fluid, V is less than V fluid, so in this case the state of the substance is subcooled or compressed liquid, and in this case we have to use table A7. Okay? In this table A7, actually each table is given at a given pressure, and this pressure for a range of temperature. At each temperature we can find actually this is at a given pressure, and at each temperature we can actually do have a list of specific volume, internal energy, enthalpy, and also entropy. So whenever we do have any of two properties, we can just go to the required table in subtable A7, and then actually we can select a certain table and we can get the other properties. So if we do have specific volumes, then we can get internal energy, enthalpy, and entropy, and all of these properties can be calculated from this table. Okay? Type this in case if I find V specific volume is less than V fluid. Type case P if I find actually this specific volume is greater than V gas. Greater than V gas means actually the state of the substance is superheated, and in this case we have to use table A6. As I said, those steps are applied for steam, and also the same can be applied for refrigerant. So in case of refrigerant, instead of going to table A6, superheated table, I will be going to table A13. However, the same steps are applied. Let's look at the third case, if we find actually that the given specific volume is greater than V fluid and less than V gas, so the state of the substance, in this case we do have saturated mixture. As we do have saturated mixture, we are in the saturation zone during the boiling process or the phase change process. So in this case, the temperature is equal to the saturation temperature, pressure is equal to the saturation pressure. So at this temperature, when we go to the table, we can get also at this temperature we can get actually the saturation temperature, and at this temperature we can get the saturation pressure, which will be the second column. If pressure is given and we go to table A5, also I can get the saturation temperature, which is the temperature of the substance at this state. And in this case, actually the next step is to calculate the value of the quality X. In this case X, we are given the value of specific property V, and we do have V fluid and V gas. So X will equal to given specific volume minus V fluid divided by VFG. VFG is V gas minus V fluid. However, there is a column in the table gives this value directly VFG, which is the difference between V gas and V fluid. But now I got X. Let's say I need to calculate actually internal energy, enthalpy or entropy. So in this case, I will be just going to the table. I got in this case V fluid, V gas. I can get actually also U fluid and U gas at the given temperature or at the given pressure. Also I can get H fluid and also I can get H gas. If required, we can calculate entropy S fluid, and also we can get from the table S gas. But if I need actually to calculate the total value, so internal energy will equal to U fluid plus X multiplied by UFG. UFG is the difference between U gas minus U fluid, and also it is given in the table. Enthalpy is equal to H fluid plus X multiplied by HFG. Entropy also is S fluid plus X multiplied by SFG. This is actually how we can calculate all of the properties. So in case A and B, just we can go to the table, either table A7 or A6, and then actually we can read the value directly, internal energy, enthalpy, entropy. But in case of the case C, we do have saturated mixture. So in this case, the specific volume is greater than V fluid and less than V gas. What we can read from the table is V fluid and V gas, all of the saturated liquid properties and all of the saturated vapor properties. And in this case, we have to use this equation in order to calculate the internal energy, the enthalpy, and the entropy, the total values. This is actually the first extreme case when we do have either temperature or pressure are given with actually one of the specific property, either a specific volume or internal energy or enthalpy, or in case of entropy. Now this is actually the first case. Given one of those properties, temperature or pressure with one of the specific properties, and this is actually how we can proceed with the solution, and how we can calculate the properties. Let's consider the second extreme case, when we do have pressure and the temperature are given in this case. So if pressure and temperature are given, we said in order to go to use the table, we have to have two independent and intensive properties. So actually in the saturated mixture zone, in this zone actually we do have the pressure and temperature are fixed during the phase change process. So the temperature is fixed to the saturation temperature, and in this case also, let's say this is the TV diagram. So temperature is fixed, and also this line represents the pressure line. So also during the phase change process from the saturated liquid state to the saturated vapor state, both temperature and pressure are fixed. And once we know the temperature value, we can actually know the value of pressure. And all of those points during the phase change process have the same pressure and same temperature. So in this case, pressure and temperature in the saturation zone are not independent. So pressure and temperature are dependent. All of the point has the same pressure and same temperature. So this means actually in this case, If we are in the saturation zone, so this means actually pressure and temperature cannot be given to specify the state of the substance as this state. So the second case, pressure and temperature are given. So if the pressure and temperature are given, this means the state of the substance cannot be what? Cannot be saturated in the saturation zone, because in the saturation zone, pressure and temperature are not independent. And in order to use the table, we have to have two independent and intensive properties. So as pressure and temperature are given, so in this case, we should be either in the subcooled zone or we should be in the superheated zone. So in this case, pressure and temperature are given, so we can just actually take this temperature and go to the table, or take this pressure and go to table A5. So if I took pressure, I will be going to table A5, and in this case, I will get from the table the saturation temperature. If I got the temperature, I will be going to table A4, and I will get actually, instead of T saturation, I will get B saturation, and then we can compare. But let's consider first of all, I will take this pressure, go to table A5, get the saturation temperature. Then in this case, we have to compare. We do have two cases. So case A, so if we find actually the given temperature is greater than the saturation temperature, T is greater than T sat, so the state of the substance in this case is superheated, and in this case we have to use table A6. We do have pressure and temperature. Table A6 is very similar to table A7. At a given pressure for a range of temperature, they give the value here of specific volume, internal energy, enthalpy, and also entropy. So as we do have pressure and temperature, then we can read the other properties, internal energy, enthalpy, or entropy. We can read the required properties. But this is the first case. So the second case, case B, if we find actually the temperature given is less than the saturation temperature, so the temperature is less than the boiling temperature or the saturation temperature, so this means the state of the substance is subcooled, and in this case we have to use table A7 in order to calculate the other properties in terms of internal energy, enthalpy, or also the entropy, if it is required. But this is actually, if we consider the first option, pressure is given, we went to the table A5, get the saturation temperature, and then we can compare with the given temperature. Also the other option can be done, so in this case using this temperature, we can go to table A4, just this is something optional, then we can get from table A4, we can get the saturation pressure, or the pressure at this temperature. Then we can compare case A. So if pressure is greater than B saturation, so in this case it is the reverse of the temperature. In this case, the state of the substance will be subcooled, and we have to use table A7. Case B, if pressure is less than B saturation at the given temperature, so in this case the state of the substance is superheated, and in this case we have to use table A6. Okay, so this is in case of pressure and temperature are given. Right, this is the second case that should be given for you. Right, let's consider a case. Let's say we are given pressure and temperature, and we have checked the case, and we find actually the state of the substance is in the subcooled zone. So in this case we have to use table A7. So let's say we have find actually the state of the substance is subcooled, and in this case we have to use table A7. We have checked this at a given pressure and a given temperature. We find the state of the substance is subcooled, so now we have to use table A7. When I go to table actually A7, you will find the first. This table actually consists of a set of sub-table. Each table actually is at a given pressure. You will find actually the first given pressure for the first table in table A7 is at 5 megapascal. Okay, so in some cases, let's say we do have a fluid existing, let's say at 1 megapascal, or let's say 200 kilopascal or something, so lower values of pressure. So in this case we don't have table. If you went to the table A7, you'll find the first table is existing at 5 megapascal. But I do have lower pressure, but at lower pressure we don't have table. So in this case we have to do the assumption that we can consider all of the properties V are equal to the saturated liquid properties at the given temperature. So V will equal to V fluid at the given temperature. And also we can consider internal energy will equal to U fluid at the given temperature. Enthalpy will equal to H fluid at the given temperature. And entropy is equal to actually S fluid at the given temperature. So at this given temperature, you can just go to table A4, you can get V fluid, you can get U fluid, H fluid, S fluid, all of these properties we can get, and then we can say actually the total specific volume is equal to this V fluid at the given temperature, and like this also we can calculate the other properties based on this assumption. But why actually we consider those properties at the given temperature, not the given pressure? So in this case, pressure and temperature are given. But in this case, we consider the properties are equal to the saturated liquid properties at the given temperature, not the given pressure, at the given temperature. Because if you look actually at the table, on the TV diagram, on the saturation curve, let's say this is the point at a given temperature. So this is actually should be the temperature line, and let's say the pressure line at this point, crossing this point, should be this line. So this is line represents the pressure line, and this line represents the temperature line on the TS diagram. So this should be at this point, so this value should be the actual specific volume. Type, we don't have table to get this value. So we say actually we can consider V fluid at this given temperature. So this is V fluid at the given temperature. But if we consider actually at the given pressure, so if you went at this pressure table A5, this value will be represented V fluid at the given pressure. So which one actually is close to the actual value? It should be V fluid at the given temperature. So that's why in case of subcooled table, and we don't have table, no table is available at this pressure value. So in this case, if we don't have table available at this low pressure value, we can consider the properties, the total properties are equal to saturated liquid properties at this given temperature. Last actually thing we have to provide the interpolation. So interpolation, when you just go to the table, let's say at a given temperature, and from this table, let's say we do have table A6 or something, at a given pressure, we do have a specific volume, enthalpy, internal energy, enthalpy, and we do have entropy. Let's say pressure and temperature are given, so I will go to just this table at a given pressure, and at a given temperature, let's say I need to read actually the enthalpy. But in this table, let's say, when you go to the table, let's say we do have at 100 degrees C, we do have the properties, and at 200 degrees C, we do have also the properties. But I need actually to calculate the properties, let's say at temperature equal to 150, which is not listed in this table. So just we do have a value, the properties at a lower temperature, and also we do have the properties at higher temperature. But we need to calculate the properties at temperature in between. So let's say in the table, this temperature, which is 100, let's say this is T1, and 200, let's call it as T2. And this temperature is T, which is 150. We need to calculate the properties at this temperature. So let's say at T1, we do have the value is H1, and here at T2, we do have enthalpy is H2, and we need to calculate H in between. So in this case, we can say, just make interpolation, we can say T1, T minus T1 divided by T2 minus T1 is the same as H minus H1 divided by H2 minus H1. So in this case, we can just say T minus T1 divided by T2 minus T1 is the same as H minus H1 divided by H2 minus H1. In this case, for this example, this T that we need to calculate at is 150. T1, let's say this is 100. So T1 is 100, and T2 is 200, and H1, H2 are just calculated from the table. At T1 we do have H1, and T2 we do have H2, and from this equation we can calculate the value of H. And this is actually what we call the interpolation. So all of this procedure are for steam, and typically we can apply it for the refrigerant 134A. But we said for refrigerant we don't have subcooled table. So in this case, if you do have refrigerant 134A, we don't have even this table A7, not even the pressure. We don't have, the whole table is not there. So in this case, if you do have refrigerant 134A in the subcooled zone, so in this case we have to use this assumption: V is equal to V fluid at the given temperature, and also like this, the other properties are equal to the saturated liquid properties at the given temperature. Okay, so that's it. Thank you.